Hello everyone, I am Alba. Welcome to Lecture 5, Binary Classification in Machine Intelligence I. In this session, we'll learn how machines can classify data into two categories, for example, spam or not spam, setosa or non-setosa. Our main goals today are to understand how we move from linear regression to logistic regression, learn how probabilities are modeled using the sigmoid function, explore how we train the model using maximum likelihood and optimize it through gradient descent, recognize how the concepts of data, model, and optimizer fit together, and how we can customize each part for logistic regression. Linear regression predicts continuous values, but for many tasks, we need to predict categories. So instead of getting any real number, we want outputs that represent probabilities between 0 and 1. That's where logistic regression comes in. It transforms a linear model into a probabilistic classifier. We'll illustrate this using the famous iris dataset. Each flower is described by 4 measurements, but we'll focus on 2, sepal length and sepal width. Our goal is to distinguish setosa from non-setosa. We imagine each flower as a point in 2D space and try to find a line that separates the two groups. The linear model outputs values from -infinity to +infinity, and that's not suitable for probabilities. The sigmoid function fixes that, bending the straight line into an S shape and mapping values to the range. Large positive values become close to 1, large negatives become close to 0, and points near 0 represent uncertainty. Once we have probabilities, we can decide if py equals 1 given x is greater than 0.5, classify as 1, otherwise classify as 0. The further a point is from the decision boundary, the more confident the model is. This gives a complete probabilistic model. The output isn't just a label, it's a probability distribution over the two possible outcomes. We then move to implementation using Python's logistic regression function. The dataset, the model, and the optimizer interact here. The data provides features and true labels. The model computes predictions using the sigmoid. The optimizer, in this case gradient descent, adjusts parameters to minimize error. Together, they form the pipeline of learning. When trained, the logistic model creates a smooth tilted boundary that separates the classes, showing not just classification but confidence levels as probabilities. Now let's understand how the model learns its parameters. We use the maximum likelihood principle. We choose the parameters that make the observed data most probable under the model logistic regression complete. It's like saying, find the theta values that best explain what we've actually seen. Now, we formalize the idea of likelihood mathematically. The likelihood function measures how probable our observed data is for a given set of parameters. We assume each sample is independent, so the total likelihood is the product of all individual probabilities. The goal is simple: find the parameter set, theta hat, that maximizes this likelihood and makes the observed data most likely. To simplify the math, we take the logarithm of the likelihood, which turns products into sums and avoids numerical issues. The resulting log likelihood function is what we maximize during training. For logistic regression, our model predicts the probability of belonging to class 1 using the sigmoid of theta transpose x, and for class 0, 1 minus that value. Each data point contributes to the total likelihood depending on whether it belongs to class 1 or 0. If the label is 1, only the first term remains. If it's 0, the second term takes over. This compact formula handles both cases in one simple expression. Now, when we sum over all data points and take the logarithm, we get the log likelihood function. This function rewards correct predictions by giving them higher values and penalizes wrong ones heavily. So, by maximizing this log likelihood, our model learns to make confident and accurate predictions. In practice, we minimize rather than maximize, so we take the negative log likelihood, also known as the binary cross-entropy loss. It penalizes incorrect and overconfident predictions and rewards correct ones. To train the model, we need derivatives, how much the output changes as we tweak parameters. The sigmoid derivative is elegant. It depends only on the sigmoid itself. Learning is fastest for uncertain points near the decision boundary. Here we calculate the gradient of the loss function. It shows how each parameter should change to reduce the error, the mathematical direction for improvement. The optimizer applies gradient descent. Theta is updated step by step in the opposite direction of the gradient. Each step slightly reduces the loss, moving closer to the best fitting parameters. The Python code demonstrates this iterative process: initializing parameters, computing predictions, calculating gradients, and updating values. While we won't go into coding details, the idea is simple. The computer learns by repeated correction until the loss stops decreasing. We start with data and define a probabilistic model. We apply the maximum likelihood principle to estimate the best parameters. We express this as a binary cross-entropy loss. We compute gradients and update parameters using gradient descent.